In this video, we're going to look at molecular polarity. In chemistry, we have two types of bonds. We have ionic bonds, and as you recall, ionic bonds are between a cation and an anion. They are between a cation and an anion. So that means they are held together by the positive and negative charges of the ions. And the charges are a result of transferring electrons. So we have a full transfer of electrons. The other type of bond is a covalent bond. And a covalent bond is between two nonmetals. So they can't be held together by charges because we know nonmetals are anions. So we would have two negative charges, and those are never going to be held together. In a covalent bond, the atoms are held together by sharing electrons. Now, how those electrons are shared between the two atoms can be different. So within the covalent bonds, we have two types of bonds. We have nonpolar covalent bonds, and this is where the electrons are shared equally. We also have polar covalent bonds. And this is where electrons are not shared equally. So we have nonpolar covalent bonds and we have polar covalent bonds. Electronegativity is the ability of an atom to make a molecule. Wait, sorry, it's the ability of an atom within that molecule to attract electrons to itself. So in that molecule, in that covalent bond, one atom can draw the electrons closer to itself than the other, and that is electronegativity. Here are all of the values of electronegativity of the elements on the periodic table. Notice that fluorine is the most electronegative, francium is the least electronegative, and electronegativity decreases as you go across the periodic table and down. So a lot of times people will think of it as going in this diagonal direction. It's going to decrease. When we look at polar versus nonpolar covalent bonds, in a polar bond, so this would be an example of a polar bond, you're going to get two ends of a molecule. You're going to get a positive end and a negative end. In a nonpolar bond, since electrons are shared equally, we do not get those two ends. So if this is exposed to some sort of current, then the negative ends of the molecule will line up so that they are close to that positive, and the positive ends of the molecule will line up so they are close to that negative. If your molecule is nonpolar, then notice it is not affected in that electric field. We can use the electronegativities, the actual values, to calculate whether a bond is going to be polar or nonpolar. So we can look at a spectrum, and 0 to 0.4 or less than zero point 0.5, this is going to be nonpolar. From 0 0.4 to 1.9, this is going to be polar. And then above 1.9 is going to be ionic. So these values, they come from delta En, the difference in electronegativity. And when you're calculating delta En, we're not concerned with which atom is more polar or more electronegative or less electronegative. We just want to look at the value, so you can think of it as taking the absolute value. If we look at our example of CH, delta En, the electronegativity for carbon is 2.5, and the electronegativity for hydrogen is 2.1. I can calculate my delta En. It is going to be equal to 2.5 minus 2.1, which is 0.4. When I look at my scale, 0 to 0.4 is nonpolar. So the CH bond is going to be nonpolar. It means that the carbon and hydrogen are going to be sharing their electrons equally. When we look at a bond between sulfur and fluorine, delta En, the electronegativity of sulfur is 2.5. The electronegativity of fluorine is 4.0. I can look at the absolute value of that, and the difference is going to be 1.5, which lies in the polar area. That means the bond between sulfur and fluorine is polar. And the way we represent that is I have sulfur and fluorine. This is the bond between sulfur and fluorine. As a result of the electrons moving towards the more electronegative atom, we have what is called a dipole moment. And we can show the dipole moment as an arrow. So the electrons from the sulfur are going to move towards the fluorine. But since we have so many arrows in chemistry, this right here, as I have it written, looks like a reaction arrow. So I'm going to put a line right here to make it known that this is an arrow showing the shift of electrons. Now, when you get that shift, remember we get the partially positive end of the molecule and then the partially negative. So this isn't a full transfer because they're still shared. So it's not a fully positive or a fully negative. It is a partially positive and partially negative. So we can show that using the symbol delta. This is lowercase delta, negative. Electrons are negatively charged. The electrons from sulfur are shifting towards the electrons of, or towards fluorine, because fluorine is more electronegative. So that means fluorine is going to have more negative things around it. They're not fully transferring to the fluorine because they are still sharing electrons, but they do shift. So we get that partially negative, which means sulfur is going to be partially positive. So you can do this with every single polar bond. And this movement of electrons, when we show that with an arrow, is called a dipole moment. So that is where you're creating those two poles, the positive end and the negative end. If we look at the delta En for nitrogen and oxygen, nitrogen is 3.0, oxygen is 3.5, so my delta En is 0.5. I can look at my chart up here. It is going to lie in the polar region. So again, this is going to be a polar molecule, or sorry, a polar bond. Nitrogen is less electronegative than oxygen. So in my polar bond, I am going to have a dipole moment that goes from the nitrogen to the oxygen, which means my oxygen is going to be partially negative, my nitrogen is going to be partially positive. Finally, let's look at HCl. The electronegativity for hydrogen is 2.1, fluorine is 4.0, so my delta En is 1.9. When we look at our table, we notice 1.9 is right on the edge of being polar or ionic. This is where you have to use your chemical common sense. Ionic means it must contain a cation. All right, it must be a metal. Hydrogen is not a metal. It is going to exist as a covalent bond when it is partnered with something. So even if my delta En, oh, I did chlorine. Well, that works. We'll just go with it. You can do HCl for fun on your own when you are bored. You're like, oh, I don't know what to do. I know, I'll look at the delta En for HCl and see if it's a polar or nonpolar bond. It's okay. I got lots of tips on how to stay not bored. So, since this can't be an ionic bond, it must be a polar bond. And I have my HF. The electrons from the hydrogen are going to shift towards the fluorine, and we will have that dipole moment, making the fluorine partially negative and the hydrogen partially positive. Now, keep in mind when we're calculating our delta En, we are just concerned with the value, not which one is more electronegative. So the negative sign doesn't really help us because we're really only looking at the magnitude. When we are assigning the partially positive and the partially negative, that's when you can look at which one is more and which one is less electronegative. Here are some more practice problems that you can do on your own so you can make sure you know the difference between a polar bond and a nonpolar bond.